Yes, sir. Yes, sir.
Okay. Okay. Thank you, first of all, for inviting me for this talk. And yeah, myself, Amit Shah, and currently I'm working as a consultant and quantum expert at Atos. And I'll be talking about QD quantum systems, most specifically. Before that, I'll go through some basics of the quantum computing. As Sam mentioned, you already have gone through some fundamentals of quantum computing, but I'll just touch upon some fundamentals of it before going into the details of my topic. That is QDIT, or multi-valued quantum computing system. That means beyond qubit systems, what you can imagine with respect to quantum computing. So let's start with the basics of quantum computing. So let's start with a small story. Okay, so back in 2015, when after finishing my masters, when I was starting my research program on quantum computing, so uh, I went to so many people, so many knowledgeable people to discuss about the future about quantum computing, and most of the person told me that quantum computing is nothing but a myth, right? Back in 2015. So I was searching for some motivation, so that I can start my work on quantum computing, but I must say I got demotivated from some of the people, because they believe that quantum computing is nothing but a myth in 2015. But as you know that in into 2023 or 2024, quantum computing is no longer a myth, right? Because everywhere you go, you yes, you can find someone who is talking about this extraordinary subject, right? So quantum computing is no longer a myth right now, and so so back in 2017, IBM came up with their first quantum computer, and after that, all the story regarding myth has gone away, right? So people started to believe that we can implement all the quantum algorithms on quantum computer, and people started to working on the implementation part of it, right? So quantum computing has become a well established domain among the researchers for the quantum advantage compared to its classical counterpart. So it's no longer a myth, but a new myth has arrived regarding quantum computing. And what is it? So the biggest myth related to quantum computing is that quantum computing can solve any problem in the world with blink of an eye. So this is the biggest myth currently we can heard of, right? Because people believe that quantum computer can solve any problem, any computational problem, whether it is hard or simple. A quantum computer can solve any problem with blink of an eye. But it's a big no, right? Because it cannot be possible with the current quantum computer, or maybe if quantum computer we will have a scalable quantum computer in future, it won't be possible. That already been demonstrated by the researchers. So what is it actually? What the quantum computing is? That is the main question we have right now. So quantum computing is a promise. Okay, it's not a kind of thing, or it's not a rocket science that can solve any problem, but it's a promise that some of the complex problems from the computational paradigm, right? Some of the computational problem can be solved with more faster way as compared to the today's most powerful supercomputer. That is the promise which is served from the quantum community, that you can solve some of the complex computational problems with faster way, right, as compared to the today's most powerful supercomputer. So how quantum computer can do that? I hope you have gone through the fundamentals, so you have the knowledge how quantum computer is making that difference from the classical computer or the today's supercomputer. But I'll touch upon some of the quantum mechanical properties of it, so that you will have no uh, you'll have the idea of it, right? So it will massively reduce the complexity of some problems currently intractable to classical computers. That you have already, I think, that is already being known to you, right? Because some of the problems cannot be addressed with the today's classical computers because of the lack of memory or lack of computational power. But quantum computer promises that when it will be scalable enough, it can solve that problem with maybe blink of an eye, right? So what are the problems actually we are looking for? Like, what are the problems we can target with the quantum computer, right? So this is the graph we may follow, right? So this is the computational classes. So let's start with this class. So this is the class of P. We all know that this is a polynomial class, and these problems which belong to this class can be addressed through our classical computers. We don't have much problem to solve this problem with the classical computers, because with the polynomial time we can solve these problems very easily with the classical computer. The next complexity class is the NP class, non-deterministic polynomial class. So and there is a class of NP complete, or beyond that NP hard, maybe P space or NP space. So these are the problems which are really hard to solve with the today's current supercomputer or the classical computer, right? Because uh, because we need some exponential time to solve this classes problems. So you can see that here is another class, that is BQP class, bounded error quantum polynomial time solvable problems. So some of the NP problems, or maybe NP intermediate, I can say, like some of the NP problems can be solved polynomially with the help of quantum computer, but there will be some error, right? And those problems can get a sit in this particular problem classes, right? So but we don't have any algorithm, rather I should say quantum algorithm, which can solve the NP complete classes problem in polynomial time. That is why we cannot say that with the help of quantum computer we can exhibit that P equals to NP, right? Because we know that if any problem from this class can be solved with polynomial time, then we can say that P equals to NP. But that hasn't been possible yet with the quantum computer, and researchers started to believe that it won't be possible, because there are some limitation with the quantum computer also, and for that it won't be possible to solve this NP complete problems with polynomial time with the help of quantum computer, right? So I know this is a post-lunch session, and I know what happens to the post-lunch session. So if anyone has any query regarding my slides or anything you have in your mind, you are open to say that, right? So that the talk so that it can be a interactive session, because post-lunch session is very much difficult to go on, right? I think you have understood that what are the problems we are actually trying to address through quantum computers, and obviously we are not going to solve this polynomial classes problem with quantum computers, because classical computers are enough to solve this polynomial classes problem. So our target is to solve some NP problems, or NP complete problems, or NP hard problems with some speed up, right? So let's go through with a graphical representation what are the problems we are actually targeting. So you can see, you can observe that for some p feasible, like log n or n squared time problems can be solved with classical computers. We don't require any quantum computer for that. But in case of exponential time problems which require exponential time, these are not feasible for classical computers or the supercomputers, right? And for that quantum computer can give us some time complexity advantage. Maybe it is a quadratic, or maybe it is super polynomial, right? So that we can solve this exponential problem with like polynomial time, or maybe some reduction we can get from those exponential problems. So I think you have understood what are the problems we are actually addressing. Not all the problems, right? We are only addressing the harder problems, computationally harder problems, so that we can get some advantage of it, right? So I'll quickly go through these concepts, what are the fundamental quantum mechanical properties we have in quantum computing. Let's start with the qubits first, right? So like classical bit, we know everyone that in classical bit we can store a 0 or 1 value. Similarly, we can have this qubit in quantum paradigm, which can store 0 and 1 simultaneously. So that is the extraordinary feature that quantum computing has, right? Because we know that classical bit cannot store 0 and 1 simultaneously. Either it can be 0 or it can be 1. But qubit can store 0 and 1 simultaneously. Yes, it is probabilistic. Maybe some probability 0, some probability 1. It's a unit operation. That means the summation of the probability of getting 0 and 1 must be 1, right? So it's a probabilistic thing, but it's a damn good thing that qubit can store 0 and 1 simultaneously. And for that reason, we can have some extra advantage while we are solving some computational problems as compared to the classical computation, right? So here you can see that n qubits can store 2 to the power n information. That is quite obvious, because it can store 0 and 1 simultaneously. So n qubits can have 2 to the power n information. The next next quantum mechanical property is the state superposition and the measurement, right? So state superposition is nothing but if you coin a toss, so it is either head or tail, right? When you are measuring it, it is going to be either head or tail. But when it is in the air, so it is in the superposition manner, right? That means uh, when that coin is in your hand, and that is a classical information. Either it can be shown as head or tail. But whenever you are tossing the coin and it is in the air, that becomes a superposition state, right? Because you don't know what will be the outcome. It could be 0 or it could be 1. The probability of getting 0 is half. The probability of getting I mean, the probability of getting head is half, the probability of getting tail is half, right? That means when it is in the air, it is in quantum superposition state. That means half probability with head, half probability with tail. When you are trying to catch that catch that coin again and you are trying to measure it. That means you are opening your hand and you are just trying to measure that what is the outcome of that coin, and that time you will get the uh, you'll get the actual outcome, whether it is head or it is tail. That means with one probability head or one probability tail. That means when you have started your coin tossing, the state is in classical state. Either it is on it is either it is in head or a tail, right? When you have uh, tossed a coin, it is when it is in the air, that becomes a quantum state. Either it is head or either or it is tail, right? When you are measuring it on your hand again, then it becomes again classical, and you are getting your outcome. Either it is head or it is tail, right? So this is the concept of the superposition. And similarly, we can have these qubits, what I mentioned earlier. These qubits can be in superposition manner. That means it can have a zero or a one state, or zero and one state simultaneously, so it becomes a superposition. And the last fundamental quantum mechanical property is quantum entanglement. So these four, like qubit, superposition, measurement, and quantum entanglement, make the quantum computing make quantum computing different from the classical computer, because classical computer doesn't have this qubit operation, doesn't have superposition, doesn't have measurement operation, doesn't have quantum entanglement property. Now we'll look into the quantum entanglement. So what is quantum entanglement? So as per the definition, quantum entanglement means if two qubits or two quantum systems uh, are very far from each other, right? Are very far from each other. But if they are entangled, they are correlated in such a way so that if you try to change some of the state on one qubit, that will affect the other qubit as well. So it so so for the simplicity sake, I can give an example, right? Suppose we have two friends, uh, and they are very much they are like best friends, okay, and they are very much correlated, so that if and they are like someone is in Kolkata, someone is in England, right? And they are asked the same question at the same time, okay, by some different people, and they are correlated in such a way so that if someone is giving the answer, if someone is giving the answer, and other one is repeating the same, okay, so that much correlation they have. And for this entanglement property, how much they are far from each other, but they are giving the same answer or the opposite answer as per the requirement, because they are correlated so much. So for these four properties, quantum mechanical properties, quantum computing can give the speed up or the advantage over the classical algorithms. So let's take an simple example, okay. So here are four cards, and these are four king. I know, I believe everyone knows about this playing cards, right? So we have four king, and we have to find out the king of hearts. So this is the hearts, and we have to find out the king of hearts. So we all know that for a classical computer, at time zero we don't know any of the information from these four cards. At time one, we'll unveil the first card, and we'll know the outcome of it, and this is a king of spade. Next, at time t2, it is a king of diamonds. At time t3, it is king of clubs. And finally, at time 4, we find the king of hearts. That is the mark state, right? So in case of classical computer, we need only one resource, and but the worst time complexity is 4 unit time. So that is a simple thing, like linear search, right? So worst case is 4 unit. So for a parallel computer or for a supercomputer, right? So what would be the outcome at time one? So at time one, we'll have all the outcome, because parallelly we can process, parallelly we can open this cards. But the resources has become 4 from 1, as we have shown in case of classical computer, right? The resources has become 4, time has become 1. So in case of classical, it was resources 1 and time was 4 unit. But in case of parallel computer, resources has become 4, time has become 1 unit. Now let's come to the interest of quantum computer. Okay, so at time 0, we don't have any idea what is going on. At time 1, we have all the outcome of from that from the set of cards, right? At time 1, we know that king of hearts is there. But and for that, resources required is resource required is 1, because only one quantum computer is enough to find out where is my king of hearts. But time is 2 unit, right? So you should have a question, how? I mean, uh, i'm I'm telling you that at time 1, uh, I can unveil all the cards. So why you are telling the time unit is 2, right? So let's 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 get little mathematical. Okay, so suppose we have a quantum state. So this is a Kate notation. I think you have already gone through this Kate notation. This is a psi state, and we have probabilistic king of cards, right? Like 1 over root 4 amplitude of king of spades. Similarly, 1 over root 4 king of diamonds, king of clubs, king of hearts. That means if we want to measure at time 1, the outcome will be 1 by 4, right? 1 by 4 of king of hearts. But you cannot distinguish, right? Because all the outcome is 1 by 4 at time equals to 1, right? So that is why we need to iterate this algorithm for root over of 4 times, as we have four number of cards. That means if we iterate this algorithm for 2 times, we'll have king of hearts with one probability. So that is why it is taking 2 unit of time to give us the actual outcome of king of hearts, not the 1 unit of time. So if we compare with the classical computer and the supercomputer, so in case of classical computer, we need one resource 1, but the time complexity is 4, because was time complexity, it's nothing but a linear search. And in case of parallel computing, the resources have become 4, and the time unit is 1. So we have a good time complexity for the parallel processing. But in case of quantum computer, we need one resource, but the time is 2, right? So 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 now look it look in look this I mean now observe this in a bigger picture. This thing, suppose we have so the time complexity for classical computer, right? For the time complexity for classical computer has scaled up to, right, like exponential, because you have if you have 2 to the power n number of cards, it will become 2 to the power n number of time unit, right? In case of 2 to the power n number of cards, the resources will be like 2 to the power n number of resources. That is not feasible. That is why that is why parallel computers or the supercomputers have the limitation, because if it becomes like 2 to the power 100, it cannot be possible to have 2 to the power 100 number of computers parallelly to complete your computational problem, right? So it becomes infeasible. But in case of quantum computer, as you have observed, that if you have one number of resource, and it will become the root over of number of cards, right? So if you have 2 to the power n number of cards, the time complexity will be like 2 to the power n by 2. That is quadratic speed up as compared to the classical and the classical computer, right? So that is the advantage. And because of this quantum state, because of these qubits, that is why it can be superposed in such a way that all the cards will have same probability or equal probability, and with the help of this iterative process and through some entanglement, and I'm showing the Grover's algorithm, simple form of Grover's algorithm, and we can have an algorithm with quadratic speed up for a simple search problem, right? So I think you now have the clear motivation why we are going to use quantum computer in future, right? Because it is giving the quantum advantage, it is giving the advantage over time complexity for the computational problems. So as I already mentioned that it is giving the quadratic speed up, that is the quadratic that is square root, you can observe, right? And this is the mathematical part of the motivation. Now let's come to the point of application related motivation, because I belong to industry, and we have to be more specific about the quantum applications, because that will accelerate the research as well. So if you have any question up to this point, you can ask me. If you have any query, any question, anything you have in your mind. Okay. So
Sir,
why in yes, yes, sure, sure.
is there an example of an NP problem that can't be solved using quantum computers?
Yeah, NP problem. So we have Shor's algorithm, right? Have you heard about Shor's algorithm?
Yes, sir.
So a Shor's algorithm, what actually it does, a Shor's algorithm, it's a factorization problem, right? So it's a prime factorization problem. So if you know RSA algorithm.
No, sir.
Okay, for time being, you just try to understand that whatever transactions you are doing, whatever password you are giving in your Facebook or uh, any other account, in the background RSA crypto system is going on, right? And for that, for a hacker, uh, it takes almost 2 to the power n times to break that password, or the transaction you are doing. And if you have a quantum computer, you can crack that password with n cube. That is nothing but a polynomial time solvable problem. That is, with n cube possibilities, you can break that password, that RSA crypto system. And with the help of the superposition and entanglement property, in 1993, MIT professor Peter Shor showed that we can uh, factorize a number with two, which is a cofactor of two prime numbers, and it can be solvable with n cube time, that is polynomial time, but with some error, like half of the times you will get the actual outcome, half of the times you will fail, right? So that is it is it is belong to the it belongs to the BQP, that is bounded error quantum polynomial time.
Okay, so
Okay. Anything any other question? Okay. So why investing in quantum computing now? Because so we all know that this is the era of artificial intelligence and machine learning, right? And we know that to do this artificial intelligence or machine learning or neural network, you need so much of memory, so much of processing, and quantum computer can give that processing power to the user, so that they can implement their algorithm with some ease. So if we can amalgamate this artificial intelligence with the quantum computation, yeah, it's a win-win situation for everyone, right? So, and there are multiple numerous application you will find in the industry, like from manufacturing to public sector or financial service, telecom, resources, healthcare, everywhere you will go, you will find some optimization problem, and you can solve those optimization problems with the quantum computer. So you'll find lot of applications in case of quantum computing. In chemistry also, that I haven't mentioned. So in chemistry we know that the molecules structure and other stuffs are very much complicated. Today's quantum computer fails to determine those molecular structure and all, but with scalable quantum computer, it is believed that those problems can be solved with better way, right? With respect to time, with respect to memory constraint. And in case of pharmaceutical, many players have already invested so much money on quantum computing, right, to solve to solve uh, various complicated complex problems related to pharmaceutical. And after COVID, we all know that it is very much required, because it is very difficult to predict the DNA structure and protein structure and all, to find out the actual medicine for a complex disease like COVID and other viruses, right? So that is why people are investing so much on quantum computing. Cryptography, as you have asked me that question, because cryptography is one of the main domain that gonna rule in this decade, in the I maybe down the line 2 to 3 years. Quantum communication and quantum cryptography is going to be the future in India, before quantum computing, I believe, because it has the potential, enough potential to uh, maybe change all the paradigm in case of cryptography and communication, right? So as I mentioned, Shor came up with the algorithm, that is Shor's algorithm, in 1993, and he showed that this RSA crypto system can be breakable with n cube of time, as compared to the 2 to the power n time in classical computer, but with some error. Um, but it is huge. Like, suppose a hacker has a quantum computer, scalable quantum computer, and if he can break all the transaction passwords and Facebook passwords and any password, that is really a war, right? So we have to wait and watch what is going to happen in future with this quantum computer. Next is finance. Yes, finance related industries are investing so much money, because there are so many problems to predict, like a risk analysis we need to predict, or portfolio optimization. One of the key problem that finance industry has, right? So these are the optimization problems, and that requires a lot of computational power, and quantum computer can give that much of power to solve those problems. Oil prospection is one of the problems that can be looked into. Combinatorial optimization problems. I have told this before, actually, because I have mentioned that any optimization problems can be looked into, like any NP hard problems. Okay, because we know that those NP hard problems cannot be addressed with the supercomputers as well, because of the lack of memory, lack of computational power. And that is why companies like Amazon and other companies are investing so much on quantum computing, because they have problems like logistics, because they are solving some traveling salesman problem, vehicle routing problem. And if they get some of the advantage, maybe some little time complexity advantage, and they will be earning billion of dollars, right? So that is why they are investing so much on quantum computing, so that they can have that extra advantage as compared to the other companies regarding this problems like traveling salesman or vehicle routing problem. Okay. And the last but not the least, I think machine learning, as I already mentioned, that yes, machine learning requires so much computational power, and quantum computer can give that computational power to the machine learning problems. Any question up to this related to quantum applications, and what are the prospects in future? Maybe if you have any query, any doubt. Okay, so I believe that everyone has understood the fundamental of quantum computing. What are the quantum mechanical properties we have, which we don't have in case of classical computing, and those quantum mechanical properties this can be possible, right? So we have that knowledge. So till previous slide, I have talked about only like qubit systems. Like you have a qubit, and you can have zero or one information, and zero and one information simultaneously on your qubit. But beyond that, uh, beyond qubit systems, we can have a qubit system as well. That means we should not restrict ourselves to not only to zero or one. We can have infinite number of arity in our quantum systems, right? So let's go with the definition first. So in case of QD, with the introduction of mathematical notion of a QD, the boundaries of quantum computing are extended beyond the binary states. That's I have already discussed, right? Don't look these quantum systems as qubit only, like zero or one only. It can have like zero or one or two or three or four, anything you can imagine, because these property is inherently there on a quantum system, right? So you can imagine any information like zero, one, two, three, up to d, right? So qdt are states in a d-dimensional Hilbert space. That means our qubit system can be d-dimensional, right? And where d greater than 2, thus allowing a much larger state space. It is obvious, because if you have that much of systems like like 3, 4, or 5, or up to d, you can store larger state space with smaller number of qubits as compared to the qubits, and process information as well as simultaneous control operation. That is obvious, because if you have that much of extra information in your head, then you can parallelly operate your operations easily as compared to the qubit only systems, right? So I think this is the definition of qubit. So as I mentioned that systems are inherently qubit. That means you can implement your algorithm through qubit system on any quantum technologies that exists, right? So like I mentioned here, like spin systems or superconducting, whatever we know, like NMR systems or photonic systems, ion trap, topological, molecular, any system you can imagine by which a qubit system can be implementable. So with those technologies, we can implement this qubit system as well, right? What are the advantage we are getting? So advantage is like we can have multi-valued quantum hardware, and we will have some larger state space. We can reduce the circuit complexity because we will have some extra information apart from 0 1, so we can reduce the circuit complexity. I'll show some examples of how we can reduce the circuit complexity for a given problem. And efficiency of quantum algorithms, like efficiently we can implement this quantum algorithms with the help of qubits, right? So these are the advantage we can get while using qubit system. So here is an example of a superconducting technology for a qubit system, right? So you can observe that inherently these quantum systems are with like infinite arity. Like you can have 0 1 2 3 4 quantum states. Okay, somehow you are trying to you are trying to have only 0 or 1 by by giving extra energy from the outside, right? Because you are your yeah. So just a minute. Just give me 1 minute. Yes. So as I mentioned that uh, these systems are inherently qubit, right? And you are giving some extra energy to make them 0 1 state. That means qubit systems, right? S- So here is an example where we can see that how superconducting technology are using these qubit systems, right? To get 0 or 1, we need to have this much of energy. We need to give this much of energy for 0 or 1 states. And one more thing I want to mention here. So if we remember the electron structure very clearly, so if the ground energy level, if you imagine the ground energy level system is 0, then the 1, then 2, then 3, then 4, and whenever we are going towards going towards the nucleus, right, the error is becoming less. And this also goes for this technologies also, right? Whenever you are uh, scaling up your arity, like you are going to 2 state or 3 state, the noise has become more. So that is a disadvantage of qubit. But as I mentioned, there are several advantages while we are using qubits, like larger state space. We can reduce the circuit complexity. We can we can do a lot of multiple control operations over the qubit systems as compared to the qubit systems. But the one disadvantage that qubit system has, and that is the noise, because you are going to the higher dimensional systems, and automatically noise is getting more and more because of the higher dimensions. Okay, and and it it should be clear to all of you that we have lot of advantages, but we have only one disadvantage with the qubit system. That is, the noise has become more and more with the qubit systems, right? So we need to show some trade-off uh, between the larger state space or the circuit complexity reduction or the multi-control operation, uh, op, multi-control operation with the noise. If we can show that uh, that we are reducing our circuit uh, in such a way with the qubit system that the noise is not giving that much of effect, then it's a win-win situation for the qubit system, right? And we'll go through some of the uh, problems that our team has solved with qubit systems, and we have exhibited that with the help of qubit systems we can have less noise as compared to the qubit systems, as we are reducing the circuit depth or the circuit complexity. Okay. So some of the science related newspapers have already played big role for these qubit systems, and you can show that magazines like IEEE Spectrum or maybe Science Daily, they have already written so many things about the qubits. Maybe the qubits is the future of quantum computing, right? Whenever we'll have a scalable quantum computer, and we can have more mature technologies. In case of qubit, it will automatically give the advantage for the qubit system as well, because if we can reduce the noise of a quantum hardware, then automatically this quantum hardware is going to give advantage for this uh, qubit systems, right? So again, let's go to the basics first. Okay, let's start with the quantum circuit. I hope you already have some glances on quantum circuit. We know that uh, our we can define any quantum algorithm with quantum gate based quantum circuits, right? And quantum circuit can be defined in this manner. Like we will have some qubits, and those qubits initialized to its zero. Then we can have some single qubit gates, some multi qubit gates, and finally we'll have some measurement operation, right? So here we have some one qubit gates and multi qubit gates, and that gates and qubits uh, consist a quantum circuit, right? So with quantum circuit, we can represent or we can define any given quantum algorithm very easily. And these are the quantum gates, and these are nothing but unitary operation, because our circuit are very much reversible. That is why these gates are unitary. So here are some examples of quantum gates, some single qubit quantum gates. Let's start with the Hadamard. So Hadamard gate is nothing but a superposition gate. If we apply Hadamard gate, it gives the superposition state of a qubit, right? We can have a NOT gate or Y gate or Pauli G gate, one phase gate, maybe T gate, right? So these are the important gates that actually that that actually help us to create a quantum circuit for a given quantum algorithm, right? Some rotational gates are also there. As you if you if anyone has mm, talked about a blosphere yet? Do you know what is blosphere?
Yes, sir.
Okay, so I think you can understand what these gates are actually doing through those Bloss pair, right? Through some unitary transformation, the quantum state. So this is the initial quantum states, and we are incorporating some some of the quantum gates to evolve the quantum states from initial state to the final state, right? So and it can be visible through the matrices, and because these are nothing but vectors, and through Bloch pair you can traverse the Bloch pair through this unitary operation. So that is the main concept that is given by the Dirac, right? So these are the 1 qubit gates we have exhibited in this slide. Next gate sets are the multi-qubit gates. Okay, first one is control NOT gate. So in case of control NOT gate, if the control is 1, then only the target will flip, as you show as it is shown in the matrix as well. Swap gate does the swapping between 2 qubits information, right? Control Z actually, if the control is 1, the phase will be changed for the target qubit, and for 0 control it will do nothing. In case of Toffoli, if the two controls are 1, then only the target will flip, like here only. For all the first 6 states, like 000, 001, 010, 011, 100, 101, it will give no effect. But in case of 110, it will become 111. In case of 111, it will become 110, right? That means whenever the controls are 1, target gets flipped. Perfect. Now, whenever we are talking multi qubit gates, right? Up to 2 qubit gate, it is fine. I mean logically everything is fine. Okay, logically you can have like any multi qubit gate. You can have 10 control gate, or you can have 100 control gate, right? But physically it is impossible to implement more than 2 qubit gates. What does it mean? It means you can implement this control NOT gate, you can implement this swap gate. You need some decomposition, but you can implement this swap gate or control Z gate. But whenever you are going to implement this Toffoli gate on a real quantum hardware or a real quantum processing unit, right? You cannot implement this Toffoli gate directly on that particular quantum hardware, because there is a hardware constraint, and the constraint is you cannot implement uh, you cannot implement any gates which are not 1 qubit or 2 qubit gate, and this is a 3 qubit gate, right? The Toffoli is nothing but a 3 qubit gate. So this 3 qubit Toffoli gate needs to be decomposed in such a way so that it can have only 1 qubit or 2 qubit gates, right? So you can see that this Hadamard this T gate are the single qubit or 1 qubit gate, and this C naught are the 2 qubit gates. So one Toffoli gate has become now like eight or nine single qubit gates and 6 2 qubit gates. So it's a huge complexity, right? And in case of multi-control, more than 3 control gate, you need extra ancilla qubits also. Like if you have a 4 control qubit gates, you can see that you need 3 extra watt qubit or ancilla qubit to decompose this multi-control Toffoli gate. So you can imagine that if your algorithm has so many multi qubit gates, then the time complexity of that algorithm will automatically increase, because you need to decompose your multi-control gate first, so that you can implement those gates on a quantum hardware. So you need to use as less as possible this multi-control gates in your quantum algorithms. That is the main funda, while main funda we follow while we we actually synthesize the quantum circuit for a given problem with the help of quantum algorithm, right? Any question till this decomposition part?
No, sir.
Okay, okay, I think you got it, right? Okay. So I have talked about the quantum gates in binary systems, right? All the gates I have exhibited in past 4 slides all talked about the quantum gates in binary systems. Similarly, we can generalize these gates to the qubit systems, right? Like I have I have an example of qubit gate of X gate or NOT gate, and I have an example of G gate for a qubit system. That means you have a three-dimensional system. You can have 0, 1, 2 information in your qubit systems, right? So you can easily generalize those gates in qubit system as well, right? You don't need to uh, worry about the qubit gates. If you know the qubit gates, then you can easily generalize those qubit gates to another level of qubit systems, right? So so if I summarize whatever I have gone through for last 1 hour, so we know that what is quantum computing, right? So this is nothing but a promise that gonna solve some computational hard or complex computational problems, right? How they are going to solve with quantum advantage because of those quantum mechanical properties, and I have exhibited an example of cards, how we can have that extra advantage. Then I have talked about qubits, like we not only we can have 0 or 1 states in a qubit system, but also we can have like infinite arity 0, 1, 2, 4. And I have also talked about the quantum gates and quantum circuits, because we know that to represent or to define any quantum algorithm, you require a quantum circuit. You need to synthesize quantum circuit for that particular given quantum algorithm, right? For a specific computational problem. Then we talked about the quantum gates, and we know that beyond 2 qubit gates, it cannot be directly mapped into a quantum hardware. We need to decompose that multi-controlled gate in such a way so that it can be decomposed into 1 qubit or 2 qubit gates. Similarly, we have shown that all the qubit gates that exist in the literature, that can be generalized into any qubit systems, because only rule we have to follow that uh, those gates remain unitary operations, right? Now we'll talk about some of the applications that we have worked on in last 2 or 3 years, maybe, or 4 years, as we have entered into to 2024, right? So let's start with a simple computer science problem, that is k coloring problem, right? So k coloring problems states that if you have a k number of color, you need to color a given graph in such a way so that no two nearest neighbor vertices will have same color, right? And you have to color that graph with the given k color. And we we solved that problem with the help of a comparator. And we came up with an idea, or we came up with circuit of this k coloring problem. And we showed that it can be generalized to any dimensional quantum system, any finite dimensional quantum system, I must say. And we also compared with our uh, circuit cost estimation with the other existing works, and we showed that novel comparator uh, can give some extra benefit over the existing literature, right? So this is an example where we first showed that any computational problem like k coloring problem can be implemented in any dimensional quantum system. That means with the help of qubits, you can solve this k coloring problem on a quantum hardware. So so this is the first work that we have done. Next, we extended that work, that k coloring problem work, to the clique problem. And you know that clique is nothing but if you have a graph, and you are search now, suppose you have to search a complete graph from the subgraph of that graph, right? And suppose you have been told that you need to find out the k clique, right? That is the number of node. K is number of node, and that much of clique or that much of complete graph you need to find out from a quantum from that particular given graph, right? And we have also similarly we have shown that this problem can be implemented for any finite dimensional quantum system. Next, we came up with an idea where we have shown that quantum walk. So as per definition, quantum walk is the quantum version of classical random walk. If anyone knows about classical random walk here.
No, sir.
Okay, so let's start with the classical random walk. Okay, uh, yeah. 335. Okay, so let's start with the classical random walk. So classical random walk is a statistical method, I should say. Like suppose if you have a line of several points, okay, and from a midpoint or from some initial point, you have started to go either right or left. So if you are in a line, you are in an initial point, and if you need to go either right or either left, right? So but the problem is, like, you cannot choose randomly this way, like, oh, where should I go, like right or left? If you have a coin and you need to toss a coin, if it is head, you are going to go right. If it is tail, you need to go left. And this way, you need to coin the toss like t time. T is some time unit, and you will find out through classical random walk that uh, after t time, okay, the the probability of being in the initial point is the above of other points. Got my point? That means from where you start, right, you end up with that particular initial point as per the probability distribution. That is nothing but a Gaussian distribution. Okay, but in case of classical work, like researcher in early 2000, they showed that with the quantum coin, like the coin has become superposed coin. Okay, it is not only either 0 or 1, it is probabilistic of 0 or 1, 0 and 1, right? And with the help of quantum coin, you will find out that you have the least minimum possibility that you are in the initial point where you have started your quantum walk. You have the highest probability as the far at the far for being there. right? So that is quite amazing. It is completely opposite of classical random walk. That is why people gets interested to work on this quantum walk, because this classical random walk has many application which will blow your mind, right? Because this classical random walk has an application of page rank. So page rank used by Larry Page, right? From Google, and we we use this Google search numerous time daily, but in the background it is the classical random walk which is actually happening. And this classical random walk is trying to find out the keywords and trying to find out the uh, most most appropriate pages for you through this classical random walk. Or maybe Meta or Facebook is using to find out the probable friends in your Facebook, right, through this classical random walk. So people gets interested working on quantum walk. And we showed that this quantum walk can be efficiently implemented on a quantum hardware. And 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 we showed this in ternary system for the first time, that with the help of 0, 1 and 2 state, it can be easily implemented, or efficiently implemented, as compared to the naive quantum walk approaches uh, that exist in the literature, right? So we showed that. And after that we generalized that quantum walk approach for any dimensional quantum system. So we showed that if you go beyond that binary or ternary systems to the DRI system, you can efficiently implement this uh, quantum walk on a quantum computer, right? So these are a little complex. I should say these are little complex things to understand, because it's like a 30 to 35 pages paper, right? And to explain this papers, maybe I need another session. For every paper I need another session, another 2 hours to explain. But just for time being, you should know that with the help of QDITs, right? With the help of QDITs, we can efficiently implement or we can efficiently design uh, circuits for the computational problems like K coloring problem, or click problem, or any NP complete problem, or NP hard problems, or discrete or quantum walks, right? As I mentioned, because quantum walks have so many applications. Okay. So one thing is common in these slides, and that is the multi-control gates, right? Multi-qubit gates. You can observe that to design logically these computational problems, we require so many multi-qubit gates, right? And I have mentioned this thing that we have to eradicate this multi-control gates from our circuit as much as possible, right? So so what would be the solution? Okay, what would be the solution? So the solution, before going into the solution, let's talk about the multi-controlled or n-qubit Toffoli decomposition first. That means we had one slide on multi-control Toffoli gate, right? A slide that showed that told us that we need some extra ancilla qubits. We need some extra qubits to design or to decompose a multi-control gate, right? That means you are giving more error to the system. Whenever you are using more qubits, whenever you are using more qubits, right, you are giving more noise. The circuit complexity is becoming very high as well, right? Like maybe I can say it becomes collision of errors. So we need to find some technique to decompose this multi-control gate, right? We need to find some technique to decompose this multi-control gate in such a way so that our circuit complexity is not increased so much so that there is no feasible outcome because of the error, right? So in 2019, from USA, some researchers from from Princeton, from MIT, and from UC Chicago, led by this person Gokhale, came up with an idea, right? And that idea is nothing but intermediate QDIT approach. So you have heard about QDIT. So qubit is nothing but beyond qubit. Now you are listening intermediate qubits. So what is it? What is intermediate qubit? Before that, I just add one line here. So Gokhale showed that to decompose multi-control topology, as we mentioned 4 slides back, that we need extra number of qubits or the ancilla qubits or the working qubits. Gokhale first time showed that with the help of intermediate qubits, we don't require any extra working qubits or ancilla qubits, because you have that extra information, that two information, right? You can see that two information here. With two information, you can manipulate or you can evolve your quantum circuit in such a way so that you can decompose your Toffoli gate with the existing qubits, and as well as you can have the functionality intact. So that was like a good contribution, I must say, from the team of Gokhale. And previously it was like you need 13 qubits, 13 1 qubit or 2 qubit gates to uh, decompose these Toffolies, right? Because here you can see that we have now some Toffoli gates as well, because Toffoli is nothing but two control gates. Okay, we need to further decompose this Toffoli as well, and to decompose this Toffoli, we need extra 13 qubit gates, one qubit and two qubit gates. Okay, so we took this example and we came up with an idea later on in 2020. Before that, just let's start with the definition of intermediate qubit, right? So the definition of intermediate qubit is by simply adding a discrete energy level, we can easily have a higher dimension quantum state for temporary use. Just concentrate on this word, that temporary use, since these are present only as intermediate states in a qubit system, whereas the input and output states are qubits. Let's take an example. So here is an example of Toffoli decomposition. Okay, so let's think about, these are binary states. Only it can store 0 or 1 at the initial point, right? Now, if it is 1, it is we are using a NOT gate, or we are using a addition gate, which is actually increasing the value of this uh, qubit system, right? And if it is 0, it will become 1. If it is 1, it will become 2. That means when it is 1 and when it is 1 at the initial stage, it will become 2. And this 2 remains only in the intermediate state. you don't have these two in the initial state. Initial state only can have 0 or 1, 0 or 1, 0 or 1. These two state is storing the extra information of being 1, these controls are 1. When if and only these controls are 1, this qubit becomes 2 state. That is why it is intermediate qubit, right? Again, you are just applying the U dagger of this. That means the unitary transformation of conjugate unitary transformation of this, and this will become 1 or 0 again. That means only this 2 state is present intermediate or in temporary basis, right? So this is the concept of intermediate qubits. So initially it was 0 or 1, it was binary. At the end it is 0 or 1. In the intermediate it is only 2 state, right? And with the help of this 2 state we can decompose this Toffoli gate, right? We can decompose this Toffoli gate with only three uh, three gates, right? So as you remember, if we uh, as you remember, this Toffoli gate requires almost nine single qubit gates and 6 2 qubit gates, right? But you can decompose this Toffoli gate with the help of intermediate qubit with only 3 number of uh, 2 qubit qubit gates, right? And that is the advantage of using this intermediate qubit while we are decomposing some multi-qubit gates, right? So as I mentioned that Gokhale came up with this idea of of decomposing this multi-control Toffoli, right? But we propose we proposed this further decomposition of Toffoli and multi-control Toffoli in such a way so that it can be generalized to any finite dimensional system. So we came up this idea uh, uh, we came up with this idea in 2020, and we worked out, we communicated this paper to in 2021, then it gets published in 2022, right? So we showed that we need further decomposition of this Toffoli gate in such a way so that so that so that the depth of a circuit, depth means how many gate operation you can do in a single time frame, right? So these are the time slices. If I do some slices of time, so how many quantum operation you can perform, right? In this time slices. So we showed that our depth of the circuit while we are doing decomposition, that is logarithmic. Uh, and in case of Gokhale, it was logarithmic as well. But for further decomposition, they required 13 number of 13 number of gates. But in case of our approach, we need only 2 number of gates, because uh, initially it was 3, but after some optimization we found out that only 2 number of gates are enough to decompose this Toffoli further, right? And this the approach of Gokhale only restricted to binary, because they haven't they didn't do any further decomposition. But as we have decomposed decompose this Toffoli in such a way that it can be scaled up to any dimensional quantum system. So this is the first of its kind approach where we showed that a Toffoli gate, a NQ bit or NQ dit, any finite dimensional multi-controlled gate can be decomposed with logarithmic depth, and it was my main contribution in my PhD. Okay, so yes, so as I mentioned that it was for qubit systems. Then further we go up to DRI system, and we showed that with the help of intermediate qubits, like we need, if we are decomposing DRI Toffoli gate, okay, uh, you need to access D plus one array system and D plus two array system to two extra two extra array system. If you have the access, you can decompose your uh, you can decompose your multi-qubit gate with logarithmic depth, right? So that was the contributions we made. So after that, we numerically analyzes the success probability or the noise of the system, and we showed that our proposed decomposition is far better than the Gokhale's decomposition. We showed that in case of 50 qubits, our success probability still remain around 40%, but in case of Gokhale, it becomes becomes zero success probability. Okay, so this is the formula that that we uh, in which we do the numerical analysis. So next after that breakthrough, right? So we can say that that was a breakthrough of decomposing multi qubit gates with the help of intermediate qubits. We started to working on some application of it, right? So as you remember that in binary system, to decompose Toffoli gate, you need so many 1 qubit and 2 qubit gates. There are a lot of options available for the decomposition. I have exhibited two of them, and but we tried we replaced this decomposition technique with our technique, and and we designed all the quantum arithmetic operations with intermediate qubits, and we showed that we can design a adder like this, and the noise would be you can see that in case of our decomposition, the success probability is way higher than the conventional decomposition in case of arithmetic operation. Later on, this arithmetic operation we used to solve the finance related problem. One of the examples of finance related problem is a financial derivative pricing problem, where you need to predict some pricing for a stock like that, and for that you need some multiplier circuit, arc sine circuit, square root circuit, and all. And we showed that with the help of our proposed decomposition, it is easy. It is way better than the conventional approaches, right? And it is this qubit system, this intermediate qubit has a direct contribution to the end level applications. You can see that. Next we came up with another idea where so this is an example of a Fredkin gate. Okay, so in case of Fredkin gate, if the control is one, so there is one control and there are two targets. If the control is one, and it will swap it will swap the targets, right? If the control is one, and if it is zero, it won't affect the targets. So that is the concept of a Fredkin gate. So this Fredkin gate can be decomposed as a two C naught gate and one Toffoli gate. And as you remember, the Toffoli gate cannot be implemented on a real hardware because it is more than 2 qubit gate. So you need to decompose further. You need to decompose further this Toffoli gate, and it yields as like you need so many 1 qubit gate and 2 qubit gate to prepare a Fredkin gate, right? But if we replace our proposed approach with intermediate qubit or intermediate q tree to with this Fredkin gate, we can have like a small circuit, we can have a small circuit for this Fredkin gate. And we used this Fredkin gate for string matching problem, which is a very popular algorithm for a computer science fraternity, right? Because there are numerous algorithms for string matching we have, and this is the circuit synthesis that we have done, or we have provided for to solve this string matching problem. Uh, you can see that you can have two strings, right? And you need to or maybe a target string or a string which you need to match to that target string, and you need to define those string first in this qubit systems. You need some extra working qubits, right? Extra working qubits to for your algorithm, and you need some ancilla qubits to store the extra information. And like you can see that you are something comparing, like whenever you are applying or incorporating some CNOT gates, that means you are trying to comparing something, okay? And if it yields all one, that means if all the one comes here, and if you apply a multi-control gate here for to the output qubit and it becomes one, that means you have a match. And for that you need a cyclic shift operator, and that is the main part of this work. So cyclic shift, what does cyclic shift operator do? So it actually shifts in cyclic manner, right? And through this quantum circuit, through this Fredkin gate, we have prepared this cyclic shift operator. Like if we have the control one, it will swap, or it will swap this A and B, and as I mentioned in the Fredkin gate, right? So this Fredkin gates now can be decomposed with our approach, and we have shown that with the help of our approach, the time complexity or the query complexity has been decreased, right? So these are some classical algorithms, classical state of the arts. This is one of the quantum algorithm that been proposed earlier in the literature, but we came up with better query complexity. Like with this complexity, we can match the strings, and with this overall time complexity, we can have the total uh, 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 we can have the uh, string matching operations, right? And finally, this is the final work that I want to discuss as an application of intermediate QDIT. Okay, so 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 this is one of the hardware constraint problem that we are facing every day, who are working on quantum computing. And the problem is, like, every quantum computer comes with its quantum topology, right? Every quantum computer has their own quantum topology. So what is this topology means? That means it is some graphical structure or some graph that describes uh, that describes uh, how you can map your quantum circuit to that quantum computer, right? So suppose you have some quantum circuit like this, and you have a C naught gate. Okay, this is your C naught gate. The control is on Q0 and the target is on Q3, and you have a qubit topology. The quantum hardware is like this, that P0 is connected with P1, P1 is connected with P2, P2 is connected with P3, right? Now you have mapped your qubits to this qubit topology, like Q0 is mapped to P0, Q1 is mapped to P1, Q2 is mapped to P2, Q3 is mapped to P3, right? Now if you observe minutely, then you will find out that your Q0 is not directly connected with your Q3, right? Q0 is not directly connected with Q3. It is connected via this P1 and P2. That means it is connected via Q1 and Q2. Then how we can implement this C naught gate, right? Because they are not connected. So one solution for that is like you can insert swap gate. Like here we can do that Q0 can be swapped with Q1, then this Q1 will become Q0, Q0 will become Q1, then we need another swap like Q0 will become Q2, Q2 will become Q0, then this Q0 and this Q3 will become neighbor. Then only we can implement this C naught gate. Here you can see that this is the decomposition of swap gate, and you can see that we have applied one swap gate between Q0 and Q1, right? And after that we have incorporated another swap gate between this Q1 and Q2. Then it becomes a neighbor. This Q0 has become neighbor of Q3. Then only we can implement this C naught gate. For the reversible circuit, we need to add again this swap gates. Okay. With our intermediate QDIT approach, we came up with two new quantum gates, right? And we showed that this this circuit has an equivalent of this circuit of 5 qubit gates, right? So the depth and the number of the depth and the circuit cost has tremendously reduced, right, as compared to the naive approach. And this can be this can be extended to any DRI system, as our motivation is to make all the operation uh, generalized, right? So we showed that it can be generalized to any dimensional quantum system, and we through numerical analysis we showed that our work required a less number of gates as compared to the conventional work, and we showed that yes, the trade-off between the noise and the gates are very much good for the trade-off between noise and the gate cost is very much uh, good for our proposed work, right? And the final outcome of this swap uh, of this swap has uh, the success probability of this swap operation replacement is far better than the conventional one, right? So in this paper, we showed that the swap operation can be eradicated, like moving quantum states without swap. We don't need any swap operation if we have this intermediate high dimensional qubit concept. We can move the quantum states in between, right? So this is the last application. We have worked on other applications, but because of the time constraint, I restrict myself to this application only. And after that, before going into the next slide, so whatever noise calculation we have shown in in the last in the last slides, right? All the noise profile are taken from this NISQ era, right? So this is the era of NISQ. What does it mean? NISQ means noisy intermediate scale quantum computer, right? These quantum computers have limited number of qubits, and for that we cannot do the quantum error correction, right? We cannot do the quantum error correction, as we know that for quantum error correction we require so many extra qubits, but we do not have such number of extra qubits, right? That is why we are taking into the account that our system will have noise, and we need to design our circuit in such a way so that the circuit complexity gets reduced. So these applications are completely NISQ era applications, where we showed that without quantum error correction, our intermediate qubit approach is far better than the qubit only approach, right? But what about the error correction, right? When the number of qubits will grow up, when the scalable quantum computer will be in our hand, what will happen to this intermediate qubit approach? Is is this approach still uh, will this approach still give the benefit that is giving right now in this NISQ era? That is the question we have. And for that we came up with this paper. And uh, and this paper just accepted last week in quantum information processing. And and we showed that this Toffoli get decomposition will be useful in the early quantum error correction era as well, right? Because we came up with this inequality equation, where we showed that this much of gate cost will give the benefit, while we are going to do the trade-off between the noise and the gate complexity. And we showed that in the early quantum error era, it will definitely give the extra benefit as compared to the qubit only work. But what about the fault tolerance, right? So anyone knows about fault tolerance here? Has anyone mentioned about fault tolerance, fault tolerant quantum computer?
No, sir.
No. Okay. So fault tolerance means so we are now in a NISQ era, right? So there is no error correction procedure in this era because the uh, number of qubits, right? But in early quantum error correction era, there will be extra qubits, and you will perform some quantum error correction of your quantum circuit. But in case of fault tolerance era, you need to repeat this quantum error correction technique, right? You need to iterate this operation simultaneous time, because you'll have some threshold of error, right? That, what does it mean? It means that someone will tell you that I can allow this much of error, and that is the threshold you have to follow. And for that you have to iterate, or you have to incorporate number of times this quantum error correction technique, right? And then only you will achieve the fault tolerance, right? That much tolerance we can, that much fault we can tolerate, right? And for that fault tolerance technique, you again you need to uh, do some decomposition of your gates, because these are the gates which can be implemented on a quantum hardware, may not be may not be directly fault tolerant, right? You need to do further decomposition of this gates to make them fault tolerant. And unfortunately, our proposed decomposition technique, which has two gates, two type of gates. One is one control gates, one is two control gate, right? So this one control gate is very much fine. It is fault tolerant gate. We have shown through mathematical formalism that it is completely fault tolerant. But unfortunately, we have not found any fault tolerant decomposition for this to control gate yet, right? And for that reason, it still remains an open question, and maybe I'm going to invest maybe my 2 or 3 years, next 2 to 3 years, full-fledgedly to solve this question. Can we find at least one error correcting code for which we can prove that the generalized C naught gates are transversal? What does it mean? Transversal mean, if it is transversal, then it is directly fault tolerant, right? Like C naught gate, H gate, these are transversal gate, these are directly transversal gate in the qubit qubit or qubit qubit setting, right? Or in other words, can we find some further decomposition of that generalized C naught gate, that two control generalized C naught gate, to make them transversal, so that we find some decomposition, so that we can say that this is the transversal gate and you can do the fault tolerance. And until and unless we find that particular decomposition, we cannot compare with the today's state of the art, right? Because we don't know how many further gates will be required to make this gate fault tolerant. That is why this is an open question to all of you who are interested. You can look into this problem as well, that is there any decomposition of that two control C naught gate to make that gate transversal or fault tolerant, right? With that note, I'll end my today's talk, and I want to acknowledge all the collaborators, like starting from University of Calcutta, ISI, IBM Quantum, LTI Mindtree, TCG Crest, uh, NTU Singapore, all the collaborators and the interns, and they have really contributed uh, well in our works, right? And thank you. If you have any question, I would be very happy to answer all of them. Thank you. Yeah.
Excuse me, sir. Can I have a question?
Yeah, yeah, sure.
Uh, Sir, I wanted to know if to run these qubit circuits, do we have an open source available, or can we
Yes.
implement it in the Qiskit itself?
No. Qiskit doesn't have. So we have the state-of-the-art QDIT simulator. So we proposed last year, and we also we are going to patent. We are going to file a patent on this. So this is nothing but a QDIET. Okay, QUDIET platform. We proposed that platform last year, and that got published in maybe IT Quantum Communications, and we have a further updated version of it. You can find out in Google, that is QDiet,
Yes, sir.
where you can implement QDITs. and hopefully in upcoming 2 or 3 months there will be an mm, updated version of it where you'll find more you'll find Q diet more uh, what should I more efficient with time complexity, right?
Yes, sir. Thank you so much, sir.
Yeah.
Good evening, sir.
Yeah, good evening.
Sir,
Excuse
can I
me,
have a
excuse.
minute? Yeah.
Yeah, just a minute, please. So actually, may I know? Actually, I am noting down the name of the participants who are asking question. So may I know the name of the last person who queried?
Yes, sir. Myself, Mamta Prajapati, sir, research scholar from Visakhapatnam.
Okay, no issue. Okay, thank you, madam. Next, okay, go ahead. Who was asking question?
Yeah, this is Manju, sir. I'm from SRM. Sir, we do have the audiences are from different backgrounds. So, like, whenever we attend sessions, we do not know actually where to start with as a beginner to the next level and on. Obviously, we all want to solve a problem, but sir, we some says you start here. Like, when can you give us a roadmap? Actually, that would be good for
Yeah,
the
sure.
students. Yeah,
Sure,
there are
sure.
many students as
So,
well. And different backgrounds, electrical, physics. So that's why I'm asking for.
so, so let's start with a short story. Okay, so back in 2015, when I started working on quantum computing after my masters, as I mentioned earlier in my slides, so that time there was no Qiskit, there was no Google search, or there was nothing. So I had only one book, that is Nielsen Chuang. Okay, and quantum computation and quantum information and quantum computation, and that is the book I think everyone should uh, start reading who wants to work on this quantum computing, because that is the bible of quantum computing. And
Yeah,
after that
certainly this.
and after some days I found it very difficult to follow, because there were so many complex thing as well. That is why I tried to learn some quantum mechanical properties also. And and mathematically you can for mathematical aspects of quantum computing you can follow David McMahon's book. Okay, because I thoroughly gone through that book for to understand the mathematical aspects. That book has so many examples you can follow, right? And recently I forget the name. Uh, Okay, maybe I can send those books to the sir. Maybe he can forward you those books. Apart from that, as you have Qiskit now, let's start with the tutorial. Okay, because Qiskit has so many tutorials. Okay, and they have also Qiskit channel, YouTube channel. You can follow those materials also, because then only you can connect the actual properties, that actual quantum computing concepts to the application levels, right? Don't start with the programming. So I always say that to the upcoming students. They just try to do with the programming and just implement some of the algorithms and try to do some quantum machine learning rocket science thing, and that is not quantum. You need to go deep. You need to start with the books only, and the Qiskit tutorials. That will help you.
Thank you, sir. The same answer I got in 2006 when I started. Still, I don't find any material which unfolds this Nielsen. So,
Okay,
as an
so one
academician,
thing.
I feel like we really have to work on the proper documentation of this workflow. Only then I think we can like grab some people, sir. That's what I feel. So, thank
And
you. Yeah.
one thing I forget. You should start with the Umesh Bhajirani's lecture also. So Umesh Bhajirani's lecture is available in YouTube, and those are actually life-changing videos. They are very basics, and they are very. I mean, you can easily follow them.
Thank you, sir. Thank you.
Okay, thank you. So, anybody else?
So can you please repeat the name? Umesh
Uh,
Bhajan.
Bhajirani.
Umesh Bhajirani. Umesh Bhajirani. Yes, he's a
Okay.
Bhajirani
famous.
algorithm is there in quantum computing. That
Right.
Bhajirani actually approximation algorithm book is there. Yes, yes.
Right. Right.
So, thank you, sir, Dr. Amit, sir. So actually, you enlighten people and me also, because I am also doing the thing first time. Uh, so it's good for me and all the participants who are from different backgrounds. So you have like dig the thing very deep, okay, in quantum computing. So it's an opportunity for all of us to have you here uh, in this virtual environment. But still, students or the participants who wants to like have further contact with sir, I think sir will not restrict anybody to reach you. Okay.
For quantum computing, I am available for 24 into 7.
Okay, sir. So
Yeah.
I will just request you to please share your PPT with me so that I can
Okay.
provide that to the participants. So later
Yeah.
will
Yeah. I
they
can
will
do that.
benefit out of it.
Sure.
So
Sure. I
thank you,
can
sir.
do that.
Thank you, sir.
Yeah. Thank you. Thank you for inviting me.
Okay, sir. Okay, so for the
Okay. Thank you.
participants,
Bye.
today is the second session. It's over now. So we'll have the third day session starting from 10:30 tomorrow. So we'll have Professor Amlan Chakraborty from Calcutta University. He'll be giving talk on quantum machine learning. So that will be a good, uh, exciting one lecture. So I think Amit sir is a student of Amlan sir.
Right, sir.
Yes, yes. So that's good for us, all of us. So thank you for today. Okay.
Okay.
Okay. Bye.
Yeah.
Bye.
Thank you. I'm leaving. Yeah. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.